Today we are going to solve a problem related to wave motion. Now this problem will clarify a lot of aspects of how to calculate the wavelength and velocity, displacement, phase difference, and all these terms that you hear of from given data. So what we have here is the picture of a wave traveling. This picture is taken at one instant t. We don't know what that time is, but at that given time, this is the wave. So you can see here, this is the origin. Okay, so this is the origin. So origin means this is x axis. So x equal to 0 here, and these distances are given here in centimeters. So you can see here that the first point where the displacement of the wave is 0 is somewhere between 0 and 1, and this graph is y given in centimeters, and that is the displacement. Okay. Normally this displacement, which seems to be sinusoidal, that would be written as y is equal to amplitude into sine kx minus omega t plus phi. Now you remember the terms here. So this is your amplitude, this is angular frequency, this is the initial phase, and this k here is the angular wave number. Okay. Now what is the meaning of initial phase? Initial phase means when x equal to 0 and t equal to 0, you will still have some displacement. Okay. So y has some value, as you can see here. This is the point. So this is the displacement of y at time t equal to 0 and x equal to 0. So we'll assume that this picture that is given to us is at time t equal to 0. Since nothing is told about it, we can take this time as 0, and accordingly this phase, initial phase, will change. So if you had chosen a different time, then this phase would have changed. So suppose we say time t equal to 0, and you can see here displacement is minus 1. So we could conclude from here that minus 1 centimeter is equal to a sine phi. So this is how we can calculate our initial phase, provided of course we knew the amplitude. Now we do know the amplitude, right? So this is the maximum displacement. So amplitude is the maximum displacement. So this is our A, and that happens to be 2 centimeters. So in other words, we can say that sine phi is equal to minus half. So the phase, initial phase, is sine inverse of minus half. Okay. So you know that sine inverse of half is 30 degrees. So sine inverse of minus half will be minus 30 degrees. Now of course we always express phase in radians. So the radian value of that would be 30 upon 360 minus into 2 pi. So 2 pi is 360 degrees, 30, so that is 1/6, so that will be minus pi by 3. 1/6 here, no, 1/12 here, so this will be pi by 6, so that is minus pi by 6. Of course we don't need this initial phase here for the calculations that we're going to do later, which we haven't looked at yet. All I have done is I have analyzed the graph, and these are the conclusions we could reach by just looking at the values on the graph. So we know the initial phase, we know the amplitude. What else can we know? We know that from an initial displacement of 0 to the next initial displacement of 0 is half a wavelength, and then reaching back here, this is the full wavelength. So this is our wavelength, and we can see here that this is about 1, 2, 3, 4. So that is equal to 4 centimeters. So that is another thing we know. So we know the wavelength. So wavelength is 4 centimeters. And amplitude is 2 centimeters. Okay. So this is what we know. We also know that this is a sinusoidal velocity with a initial phase angle of minus pi by 6. Now let's go ahead and see the rest of the question. For the sinusoidal progressive waves shown above, wave velocity is given as 40 centimeters per second. So we know that velocity is equal to 40 centimeters per second. So that is another thing we now know. Now let's see what we have to calculate. First thing we need to calculate is frequency. So how shall we calculate frequency? So what all do we know? We know wavelength, that is equal to 4 centimeter. We know amplitude, that is equal to 2 centimeters. Velocity, that is given as 40 centimeters per second. And we need to calculate frequency. Now frequency, what relationship does it have with velocity and wavelength? So we know that velocity is wavelength into frequency. So this implies that frequency is equal to velocity upon wavelength, and from here we can substitute 40 divided by 4. So this is centimeters per second, this is centimeters, cancels out, that gives you 10 per second, that is 10 hertz. So frequency is 10 hertz. Next is the phase difference between any 2 points which are 2.5 centimeters apart. So phase difference. So if you look at any point here that has a certain phase. Phase means inside the sign, whatever value you have. So at any given time, let's say time is fixed, at a value of x, your phase is kx minus phi, this being a constant. So kx minus omega t plus phi, this is the phase of the wave at that particular point. What we have been asked is the phase difference between 2 points. So one point is, let's say, kx, other point is will be x plus 2.5. So what relationship can tell us the phase difference between them? Now one thing we know is that if you travel a distance of one wavelength, the phase difference between them will be 2 pi or 360 degrees. So if you have 2 points which are 2.5 centimeter apart, so we can say 2.5 centimeters divided by wavelength, which is 4 centimeters, that multiplied by 2 pi. So it is 2 pi per one wavelength. So for distance of 2.5, it will be equal to this. Make sure that they are in the same unit. So that centimeter and centimeter will cancel, and this could be written as 5 by 4 pi, and that's equal to 5 by 4 into 180 degrees. So if you want in degrees, and this will be our value. Okay, so you can easily calculate that. So this is done. So this is 5 by 4 pi. Next is time taken at any point for the phase to change by 60 degrees. So again we are calculating change in phase, but this time the place is fixed, that is x is constant and time is changing. So when time is changing, we know that the phase change of 2 pi happens over one time period. So how long will it take to change by 60 degrees? So this is 60 degrees. That will take the time t divided by capital T into 360 degrees. So 360 degrees requires one time period. So in this time period t, the change is 60 degrees. So that will give us t equals to 60 t upon 360. And we know our time period, which we had calculated earlier, or rather we have calculated the frequency. So the time period will be 1 over frequency. So that's equal to 60 into time period. So that will be 1 over 10 into 360. So that is 6, that is 1 upon 60 seconds. So this we have got here. So this is nothing but 1 upon 60 seconds. That's the time it will take for a phase change of 60 degrees. Now the final calculation is regarding the velocity of the particle at point P shown. So what I am going to do is, I am going to erase some portion so that I can do the calculation there. So I don't need this phase calculation here. So I will remove this. Okay. Now let's get back to the point P here. So the point P is located here. So what do you notice about this? At point P, your displacement is equal to 0. So if you look at this equation here, the displacement becomes 0 whenever the phase, that is this term in the bracket here, that phase is either, so the phase is either 0, pi, 2 pi, and so on and so forth. That is when sign becomes 0. Okay. So if we look at this graph, we can see that when time t equal to 0 and x equal to 0, we had got initial phase phi, and after some time, okay, this point here is the first time. Okay, so in this distance, at that same time, at distance x, this place here is the first time that the displacement becomes 0. So that means this refers to the phase being equal to 0. The next time it becomes 0 is here. So here the phase is pi, and here the phase is 2 pi. Okay, so this is phase is 2 pi. So remember this. So it is sine 2 pi. So y equal to a sine 2 pi. That is the displacement here. Now what you have been asked is velocity at that particle point P, velocity of the particle. The velocity of the particle is nothing but dy by del t, del y by del t. So that is partial differential. And so looking at this equation, what we get is this is minus a omega cos of this particular phase here. Now we know that this phase angle is 2 pi. So we have cos 2 pi, and that's equal to 1. So what you are left here with is minus a omega. So minus a omega, that is equal to minus a is 2 centimeters and omega is 2 pi into frequency. And we had calculated the frequency just now, that is 10. That's equal to minus 40 pi centimeters, and that's equal to minus 1.26 meters per second. This is centimeters per second. So we have got this also. So you can see here how to extract information from a given graph, what equations to use to calculate various parameters related to the wave motion, like frequency, the initial phase, the velocity at various points, and so on and so forth. And this will help you with solving more complex problems where we will need to find some related functions of the waves. So, I hope certain things have become clear in your mind about waves. In future videos, we will cover other aspects of the wave motion. So, keep looking at the postings of new videos, and we will soon come out with more videos on wave motion. Thank you very much.